All right, so we already took some mass and volume notes on, was it Friday? Or was it before that? But so what I want to do is I want to wrap this up, this mass and volume lab, and try to talk about some of the things we saw. We learned about how to graph with slopes, doing slopes on our graphs. And so really the point on Friday was that we were trying to find this relationship between mass and volume. So there's a reason why I had you guys do slope. Okay, and of course when we measure mass, we use a balance. We measure it in grams. And volume, we measure with a couple of different ways, actually, you learned about. We're going to kind of talk about that for tomorrow's quiz on a separate video we're going to make today. But so volume, if you use a graduated cylinder, it's milliliters. If you're doing it by a ruler, it's centimeters cubed. All right, so first, I want you just to look at your first graph. Okay, so this is on the front side. Okay, so the graph on the front side, we're finding different slopes. I need you guys to just volunteer. Tell me what some of your slopes were. Somebody raise their hand. At 2.5. Thank you. And so, like I said, 2.5, when we're finding the slope, we also got to think about our units. Okay, so the actual units for the slope would be the y-axis units over the x-axis, because what we did with slope was we found the rise over run, also known as the difference in y data versus the difference in x data. So what were the units that we had on our y-axis for this first graph? Yeah, on the y, what did we put on that? It was grams. Yep, we were finding the mass on the y-axis, so grams. And then what was on the x-axis? Volume. What are those units? What is it? On the front graph. The front graph was milliliters, right? Is that what you said? All right, so each of our slopes is really showing grams over milliliters. So there's one. Anybody else want to give me a number? What'd you guys get for slope on the front graph? Okay, so I went ahead and got out the lab to show you guys. Well, we went over this on the last notes. So we had mass in grams over here. We had volume in milliliters down here. We had 5 different points that we plotted somewhere around here. Whatever. Okay? And what we did was we tried to draw a best fit line through the middle of them. And I asked you, I told you guys, when you draw a best fit line, one of the things you want to ask yourself also is, should that best fit line go through the origin? Which means, should it go through 0, 0 right here? Okay? What do you guys think for this lab? In this scenario, should the best fit line go through 0, 0? Maybe why? Why it should or shouldn't? It should. Why? So you can do what? To get the accurate slope? You're correct. I will say it does go through the line of origin. But why? What does 0, 0 mean in this case? The mass and volume. If it goes through at 0.00, what is the mass? 0. What is the volume? If something doesn't have any mass, would you expect it not to have any volume and vice versa? Okay? Matter has mass and takes up space, meaning it has mass and has volume. So it should go through the line of origin. Now, in some cases, that won't be true. But in this case, it is. So I'm going to start at the line of origin, and I'm going to try to make a straight line that goes through the middle of my data. Pretend that's a straight line. All right? So this is just reviewing what was on the last notes. This stuff, by the way, is not on your quiz tomorrow. This is new stuff. It'll be on the next quiz. But once we have our best fit line, we can ignore our old points. Now we're just concerned with the line. All right? And I'm going to pick 2 points on that line that seem like they're easy to see, easy to read, if I have any of those. Here's one that meets right at an intersection, so that's easy to tell. That's a volume of, well, I didn't number my things, but let's just say they're all worth 1 on my graph. That's probably not the same as yours. Okay. All right, so this would be a volume of 7 and a mass of 6. So 7 milliliters and 6 grams. All right, and then I'll try to find another point, maybe right where it hits an intersection. Let's pretend it hits right there. That would be 3 grams and 2 milliliters. So what you do on this is you take the point farther to the right, and we're going to do rise over run. But this point over here, what I call this is I call it x2, y2. And the point that's farther to the left is going to be x1, y1. All right? So for our slope, what we do is we go y2 minus y1 over x2 minus x1. And then you can divide that and make a decimal. So some of the numbers I was seeing for volume were, I saw, so like Jade just told us, 2.5. I saw some 2.4. I think I saw 1.9. And I saw some people that had 1. Okay? What about on the back side? So on the back side, we're doing the same idea, graphing mass versus volume, but in this case, the volume was in cubic centimeters. Okay? So let's see here. What do we have for slope? Somebody raise your hand and tell me a slope. Don't be, Kanye? You got what? 0.13? 15? Okay, so again on the back side, if we have mass versus volume, it should still be grams on the top because that's our y-axis. But now on the x-axis, we have centimeters cubed. Okay. What else do we have? What do you have? 1.28? 0.28. Okay, other ones, what do we get? Odessa, what'd you get for the backside slope? You got 1? Okay, and correct me if I'm wrong, but that was also the slope you had from the front side, wasn't it? So on the front side, you had grams per milliliter. You said the slope was 1 gram over milliliters. On the back, you said it's 1 gram over cubic centimeters. So what does that tell us about the relationship between, first of all, volume units? What do you think that tells us about the volume units, milliliter and centimeter cubed? If both, let's pretend that both slopes are the same. Okay, both the front graph and back graph. And I'll tell you, they should have been. They should have been actually the same. A lot of people sleeping today. How do you come? So, hey, focus, think. If the slope is on the front is the same as on the back, what does that say about our volume units? They're equal. That's right. Very good, thank you. 1 milliliter is equal to 1 cubic centimeter. So as a matter of fact, like I had mentioned when we went over volume units, I'm going to put a star next to this, asterisk, whatever, important. So you got to know that relationship. Remember that I told you if you watch like medical TV shows or something like that, you might hear that cc term. Okay, cubic centimeters, give the patient 5 cc's of this, whatever. Cubic centimeters we use actually to measure 3 different sides of a solid, but what they're giving them in terms of medication is not a solid. It's something probably going in their IV. Okay, it's a liquid. So really when they say give the patient 5 cc's, they're saying 5 milliliters. Okay, so that's important to know that. And we also have to know what this slope in this lab the other main concept. What it means. Okay, so we know that in one case it was grams over milliliters. Or in the second graph, it was grams over cubic centimeters, which we now know those two terms, milliliter and cubic centimeter, are interchangeable now. All right, so what do you think that line, that best fit line, if we find the slope of it, what do you think that represents? Any idea? Jerry, I think you started to tell me about it before. What do we think that slope represents? It is a rise over run, which means in this case, grams over milliliters. You do know this. What do you guys think this represents? Any terms you've ever heard of for grams per milliliter or grams per cubic centimeter? It is. So this is the new thing you got to know is density. So if I have a graph that's showing the relationship between mass and volume, it's talking about density. What density explains is how compact the particles are. Okay? So that means, like, if we talk about mass and volume, mass being the amount of matter in an object in grams, and volume being the amount of space the object takes up in cubic centimeters or milliliters, whatever it is we're using. So we can have really, really big things that have low mass, that are, in terms of thinking about weight and mass, that have low weight. Like we could have a big balloon, but it doesn't have a lot of mass. We can also have very small things that weigh a ton, or I should say very small things that have a really high mass. What that tells me is that small object with its small volume has a lot of particles in there. Okay, so if I was to draw these, here's a I'll draw two objects that are the same volume. Pretend these cubes are the same size. But if I had one that just had like 3 particles in it, compared to one that has 6 particles, this would be more dense. Okay? If I have, here's a small volume compared to a large volume, but this one has 4 particles in it. Which one has more compact particles? Okay. Now let's look at this. Forgot what I was going to draw. I had an idea. Okay, here it is. So now, what if I do this? Let's say 2 volumes that are the same. Oh, no. Keep forgetting this. Sorry, different volumes. Okay, so I have different volumes, different amount of space. But I put the same number of particles in each one. So this has 4, and this has 4. Which one would be more dense? The smaller one. The particles are more compact. So if we put density just into a definition of, for math, okay, density is mass divided by volume. Okay, so the mass is going to be in grams, the volume is going to be in milliliters or centimeters cubed. Therefore, our units for density are either grams per milliliter or grams per cubic centimeter. And I will tell you that for this lab, water, the density, under standard conditions, has a density of 1 gram per milliliter or 1 gram per cubic centimeter. I'm going to have to move your quiz to Wednesday now so I can review tomorrow. Goodness. Okay, before you leave, you're going to hang on to those notes. You're going to turn your mass and volume labs into the tray, and then we're done.